All right, everybody, welcome back to another day of invertebrate zoology. Today we are getting into the subphylum Chelicerata. Uh, a lot of times you'll hear it pronounced Chelicerata. It's fine. You're not going to get kicked out of the invertebrates club. Typically, though, whenever we see that CH, it usually is pronounced as a K sound. So Chelicerata is where we land today. Huge group here. And arguably one of the most I don't want to say underappreciated, uh, under recognized, unshouted out groups here with the mites. Um, yes, we know in chelicerates, everybody gives the focus and emphasis on spiders and scorpions. Horseshoe crabs are a cool accessory animal, but even if you don't want to work with invertebrates, mites and ticks make up a huge part of what you probably want to work with. Um, Dealing with, again, a lot of people coming into a program like this want to start off with giant mammalian megafauna. Your mites and ticks are like a huge part of that everyday husbandry aspect. Um, and so the chelicerates are important to look at. Even if you don't want to care for them, you want to eliminate them, they're still going to be part of your daily routine. Anybody that's taking care of horses, horses especially, but dogs too, any kind of local Colorado fauna has to deal with ticks and mites. We don't get it nearly as bad here because of the seasonal changes we get. The warmer you get, where it stays warm year round, mites and ticks become a much bigger problem because we don't have that kind of winter kill off or die off that we would typically see. So even if you don't want to work with chelicerates in general, you're gonna work with them. They're going to be a huge integral part of your job. Horseshoe crabs up here on the top left. Again, I call them accessory animals, and that's typically how they're exhibited and displayed. There's a lot more that goes into them. They for sure are the outliers here in the group of chelicerates because everything else we talk about is terrestrial. But definitely warrant their own piece of lecture. So we're going to kind of start off with them. Mites, scorpions, tarantulas. They're not showstoppers when it comes to display animals, but they are relevant. And like I said, I think that the fact that places like the Butterfly Pavilion are becoming so both efficient and good at their jobs, writing AZA manuals, really kind of planting the flag in the ground for, hey, we're relevant too, speaks volumes for the fact that invertebrate species are kind of on the uprise, on the uptick. They're being exhibited more, displayed more, entire buildings built around them. And so chelicerates definitely fill a huge niche void for invertebrates because what a lot of people are interested in, even if they're creeped out by them, they're still interested. And so because of that, we need to understand the husbandry and also the education aspect. What can we talk to our guests about? Because I personally think they moved on from that accessory animal category and very much come into a league of their own. With most of our chelicerates, again, horseshoe crabs being the major exception, they're almost all going to be terrestrial. Certainly some are arboreal, meaning they live in the trees. They're never going to come down. But extremely diverse subphylum here with the chelicerates. One of the first things that we're going to look at is the body portions, and this is what separates them from the rest of the insects. Think back even to the junior high days when you're talking about what makes an insect an insect. One of the first things on there is 3 body segments. You have a head, a thorax, and an abdomen. That's kind of your go-to. Again, we could take this all the way back to the bow plan initially, right? That initial body setup. Here, though, we have 2 tagmata or tagma. The term tagma just defines different body segments. Right here is the key. This is what we're looking at that's a little different. And that's the cephalothorax. Cephala meaning head, and thorax obviously here. Because we have one piece, one shield that covers this entire segment, we unify the terms for that. So instead of cephalic, meaning head, and thorax being the midsection, we have the cephalothorax of the combination of head and mid-body, if you will. Couple important things to note here. And we're going to see diagrams of this later too, and we'll talk about it all day. But you can see in this picture, the animal looks like it has limbs sprouting out from all across the body. But if there's ever limb attachment as far as a locomotory appendage, it's always going to be located and attached to the thorax. Does that make sense to everybody? Like, it looks like, yes, the legs run rampant across the body. It's all attached to the thorax. We don't have animals with limbs from the abdomen or the head. It might look like that based off how they're splayed out, but all limb attachments happen at the thorax. If there's a limb attached somewhere else, it serves a different purpose. It's not going to be locomotory. It's going to be very, very specialized. So again, huge, diverse array of taxa here. Tons of genre exhibiting that iconic 8 legs, but always, always, always going to be centralized and attached to that thorax. If it's attached anywhere else, it's a different appendage with a different function. When it comes to the body itself, we're not going to have antennae. We lose that tactile advantage, but we replace it with multiple eyes. These typically are called ocelli. Ocelli, all right, to put this easily, typically we have 2 eyes that are compound. So think of them like your eyes. Not nearly as advanced, but the way we see color, depth, things like that, then it's typically going to be surrounded with 4 ocelli, which are simple eyes. These basically, these do the job of detecting movement, shadows, things like that. You're never going to get great detail, but you get the stimuli response you need from your surroundings, from the environment. So 2 compound eyes and typically 4, sometimes 8 ocelli, which are really there just to pick up, again, your, let's say in this case, a spider, you're very low to the ground. One of the things you want to always be on the lookout for is shadows from above. This is the same way that a fly would work. You guys ever notice how hard it is to swat a fly in your house? It's because they have millions and millions of what are called ommatidia, but make up ocelli. It's what detects something. You don't know what it is yet because you can't make the form out, but you know something's about to crash down on you, time to jump away or fly away. And so we have these simple eyes surrounding a complex eye, which gives them a really distinct advantage when it comes to the field of vision they exhibit. With the front portion of the cephalothorax, it brings us to what gives these animals their name, the chelae. This is, and again, if you think back from things we've talked about, they differ here from the mandibulates. Mandibulata makes up all that group of kind of masticating or chewing insects. Almost all of your insects fall under mandibulata. It's because they have primitive, but mouth parts, jaws. That's what separates the mandibulates from the chelicerates here. And the chelicerates, again, anytime when we talk invertebrate zoology, when we say that term primitive, you know that it doesn't mean worse. They've been doing it a long time and a lot better than most other species. So while this is a more primitive form, it's definitely effective. I don't think I need a show of hands to tell how many of you have seen a spider in your house. Like, they've made do. They get around. They get by just fine. So the chelicerate model is very effective. But here we have 3 different styles of appendages. And while 1, maybe 2, maybe all 3 you assume you know what we're looking at. This is probably the most important part of discussing chelicerate anatomy, is identifying where and how these structures are really done. It's a little more complex than just this, look at it, here it is, here's how it goes. There's a little more to it. And the reason we focus so hard on this, identifying what structure has been modified to become the chelicerae, this is how we ID the animals. This is how we separate them from, let's say, in a couple lectures from now, decapods. So a lobster, their first set of legs, when, again, decapod meaning they have 10, their first set has been modified into that iconic lobster claw. Not the same here. We're going to have 8 limbs, and we need to start looking at basically the mouth and working our way both clockwise and counterclockwise outside of the body to figure out what limbs have been modified to create the chelicerae. That's going to tell us whether we're looking at arachnids, whether we're looking at chelicerates, decapods, other crustaceans. So I know it does seem kind of nitpicky, but we really need to figure out this feeding appendage conundrum to identify what animals we're looking at. The first here, it's highlighted in green to tie into the green top left image. This is what we call a jackknife chelicerae. This is probably the easiest one. It's obviously your spider species. Tarantulas are the easy one to use because they're larger. You can see them. This is what you would call their fangs. There are, just FYI, 2 different styles of movement, and it's based off how they're going to acquire their prey. One basically moves up and down, and one side to side. So one looks more like a pincher, the thing you'd pick up trash on the side of the road with. And then the other way it moves is obviously just vertically. And both create the same end result, but are necessary based off prey acquisition styles to change up how those chelicerae form themselves, whether they pinch out or move up and down, almost like a knife and a fork working together, where it's not chewing, you're not truly masticating anything, but it's going to start breaking stuff down. I guess a good analogy would be like mortar and pestle style. You're not able to chew, but you're able to break down or grind into a pulp, whatever species you've decided to consume and whatever organism has fallen victim to the elaborate trap you've set up. But the first one, again, I think the easiest, that's our chelicerae in the jackknife style, found in spiders, mainly tarantulas. Again, that's the easiest image. Here's where we have that differentiation between the way that the fangs work. Here you can see that just because of the placement, and I know this is a fun image for everybody to look at first thing in the day. Everybody loves to watch this while you're eating breakfast or lunch, but we got to do it. These guys need to eat too. With the image on the bottom right here, you can see that up and down position. You know how those fangs are going to move. Again, it's not the best image, but the best I could think of right now is kind of that fork and knife, where you have 2 things working together to separate, break up, I guess almost pre-chew something. You're breaking it down into smaller pieces, and in the case of all of our arachnid species, mainly liquefy something. That's what you're looking to do. With the chelicera of other spiders, we see this side to side, almost like, again, that grabber arm. This immediately, and this is important for you both for husbandry and for field studies, if you should go that route. When we see this side to side placement, we know almost, I can never say a blanket statement because we're talking about animals, but we know almost unequivocally that the animals are active hunters, meaning they go out and predate versus build the web and wait around for something to happen. This outward facing pincher style, where the fangs clip out, means that you're probably tackling and subduing prey versus waiting for them to come to you. Again, here we have, this is not to say at all that tarantulas don't make excellent hunters. They are more than capable of predating. But that up and down Chelicerate design typically lends itself to more of an ambush sit and wait predator. The forward facing fangs that move side to side like the grabber do typically tell us that the animal is much more active, probably needs more room, isn't going to build a web. Again, none of these are complete blankets. Of course, there's going to be exceptions. But we know a lot about the animal just looking on the chelicera placement. If the animal has these sideways pinching versus the up and down sawing type chelicerae, it tells us a lot about what they're going to need for a setup. More than likely, like in wolf spiders here in Colorado, very, very common. You guys have all probably had a run-in with a wolf spider, whether you liked it or not. I'm not judging if any of you smashed the wolf spider because you were scared of it. Okay, no judgment. They are wicked cool animals to work with. They're so scary, aggressive, tackle anything that moves, super fun to feed and work with. Yeah, they definitely keep things interesting. Of course, another Colorado native, all our jumping spiders that we have here. First off, do amazing courtship and mating rituals. Very colorful, typically. Super fun to find in your garden. But again, all these animals have one thing in common. You're not going to find that web left behind for them to sit and wait and ambush prey. They're out hunting actively. Tarantulas we'll talk about too. While they do typically build webs, they're not the webs you think of. It's not Charlotte's Web style, where we're waiting for something to fly into it. They almost act like tripwires. They're not sticky. They just provide a early alert system. These guys build basically a Ring doorbell, where it doesn't prevent anything, but you know what's going on, if that makes sense. They're the Ring doorbell web builders of the world. Our second type of Calais or Chelicerae is the scissor type. This right here is more than likely what everybody thought was a scorpion. I should change colors. Hang on. More than likely what everybody thought was the scorpion claw. It is not. This is typically found, it's a two segment. Here being the other segment on the bottom. Mostly found in pseudoscorpions and solifuge. Solifugi or solifuges are everybody's favorite thing. It was a big trend, especially here in Colorado with our military. Camel spiders. Camel spiders get all sorts of crazy internet hype and kind of a bad rap about them that doesn't need to be there. But this is the chelicera, again, the feeding appendage of both pseudoscorpions and solifuges. Oops. There they are. The reason we're talking about all this, look at the size of the actual Calais here. Here as well, and right here. These are the feeding appendages. This is not the equivalent of the scorpion and the pinchers or the claws that reach out. These are the chelicera. This is the mouth portion of these animals. That's the equivalent, I guess, of the jaw. So let's go back one slide. While this blue image down here on the bottom looks like a scorpion, it's not. We're talking about a completely different appendage. When we get to the other tagma of these animals, we'll discuss what scorpions really have. But this is the feeding portion. This is the mouth bits. On your bottom left, this is a pseudoscorpion. We'll talk about that briefly at the end, just because they deserve a shout out. You're not going to find a lot of pseudoscorpions exhibited at zoos. They're basically smaller than a penny and move around by hitching rides on other animals. So yeah, not super displayable. There's not a line out front to see the new pseudoscorpion exhibit, but still relevant, still cool. The camel spider. Lots of stuff to talk about here real quick. Solifugi are, I think, arguably one of the most uh, mislabeled animals out there. Uh, I'm sure everybody's seen at this point something on the internet that pops up where they're huge, as big as we usually see them overseas uh, with our military holding them up and posing with them. And while yes, they're used in some bug fights out there, um, that's about it. They're not able to kill camels. Yes, of course they have a painful bite. Look at their mouths. Um, but they're by no means these world ending dominant invertebrate species that just hasn't made it here. I've also heard a lot of rumors that they've hitched rides back here to Colorado, especially with all our armed forces so close by. They've hitched rides, uh, infiltrated troops' bags and supplies and equipment and come back. Guys, they live here in Colorado naturally. Uh, they used to be called sun spiders before everybody freaked out and the camel spider craze took off. Um, they used to be called sun spiders, and they get a, I don't want to say a bad rap. It's definitely warranted because they're horrifying monsters, but they definitely don't deserve as bad of a rap as they've got. They did not hitch a ride back here. They naturally occur in Colorado. They're a native species. They're not invasive. They're not taking anything over. Uh, on the other side of things, however, uh, they do have some characteristics that make them more displeasing than others. Like, I don't think anybody here is super excited about the prospect of keeping scorpions and tarantulas for a living. I like it, but it's not for everyone. Camel spiders take it one step further. Uh, they can audibly scream, which is not pleasant. They do this crazy like banshee shriek at you. Uh, that doesn't go over well. They also have this terrible tendency, which again, I'm telling you guys all this now so that you can educate in the future. Because you'll get all these people like, oh, I've seen one of those in my house. I had to smash it immediately. It ran towards me screaming, which, yeah, I get it. I'm not going to knock anybody for having to take one of these things out because it came at you screaming. Um, I think that's a perfectly normal, visceral human reaction. But uh, these animals spend a majority of their lives hunkered down in between rocks or underneath something. And so, one of the weird, to their own detriment, things they do when they get scared is you, a giant 5 to 7 foot tall human, comes stumbling along. And their first instinct is to scream for a threat display and then hide under a shadow. Guess what you cast, giant human? A big shadow. So they actually try to run under your boots or run into your shadow, which of course gives the image that they're screaming and doing a Last of the Mohicans war cry coming at you, which does give a much more threatening first impression of them than they really are. They're really like screaming for their lives and trying to run and hide under something. But yeah, I'm not expecting you guys to, when you're out or if you find one in your house, which I have, it's crazy. It'll wake you up. Um, yeah, they don't give off the best first impression. I'm not expecting you to go back through your notes as this camel spider is yelling and running towards you, shrieking, trying to get underneath your foot. It does very much seem like a rallying war cry, but that's not the case with these animals. Just so you know, just a spot to educate. Again, not like we're not going to have a test in class to see who will let the camel spider attack them and run underneath their feet. It's exactly where most people want them, is flat underneath their boots. I understand, but just know they're more scared of us than we are of them. Hard to believe looking at that beautiful face up here at the top left, but it is very true. Moving on to our third group of Calais, the 3-segment Chelicera. This is considered the most primitive. And again, as I said earlier, primitive doesn't mean bad, very effective. It's kind of like, I guess, take phones, for example. back in the day, it used to be a flip phone or the cool phones from like the Matrix that flipped out and had 4 parts you had to unfold. Uh, Primitive, more advanced. The more advanced has simplified everything, kind of like the equivalent of a flip phone versus a iPhone nowadays, um, or an Android. Don't want to single anybody out. Uh, the simplicity of solidifying everything into one Calais is the evolutionary steps. This is the most primitive, but it does not make it by any means the least effective. Um, this is what we're going to find in scorpions and opiliones. Those of you that have taken animal bio, opiliones are your harvestmen. Most of you probably grew up calling them daddy long legs. Everybody has, hopefully, if you don't, I don't know what to tell you about your childhood. Um, Hopefully everybody has an experience with daddy long legs. They're kind of iconic. Has anybody noticed they've disappeared quite a bit lately? They used to be around a lot more. There's reasons for that. Um, yeah, if you grew up around here, you more than likely grew up seeing a lot of daddy long legs. Not as much anymore. Uh, but these are harvestmen. They're not true spiders. Harvestmen, and we'll talk about them in a second, but they get another weird rap similar to camel spiders that is very undeserved. So here, let's highlight this, not pedipalps. That's the other term we're going to learn, where the pedipalps are versus the chelicera. The chelicera are the feeding appendages. The pedipalps are going to be the first, or next, I guess, outside. So if we start here at the midline, these are the chelicera. The next appendage out is going to be the pedipalps. This is where that iconic kind of scorpion claw comes from. The pedipalps on a tarantula, those are going to be used almost like fingers to manipulate prey. They're not legs. They're not locomotory, and they don't serve a feeding purpose. It's usually prey manipulation or acquisition. The chelicera are the feeding appendages. The reason we're pointing all this out is because of animals like this, the long-legged harvestman. Crazy cool looking animal. Would probably horrify most of you if you ever saw it. Looks like a spider-scorpion combination monster. And the distinction I need you to make here is, again, when we're looking at that bow plan, what modifications have occurred with this animal and what are we really looking at? Because yes, this does look like something cooked up in a lab. An animal with these huge pinchers, but we got to notice there's 4 pairs of locomotory appendages, 8 legs. So we know it's not a leg that's modified. Otherwise, this would be a lobster. It'd be a decapod. When we realize that these are in fact the chelae, that tells us a lot about this animal. Another great example here. So we're going to stop on this picture for a second, just to talk about the anatomy. The breakdown of this animal. Let's do this from a field research scientific standpoint. We want to find out if it's an arachnid or a decapod. Arachnid or chelicerate, you'd have 8 legs. 1, 2, 3, 4. So we've got 4 pairs of jointed legs. That makes you an arachnid. We know that this isn't a leg, but what the heck are these things? This is where that breakdown, and the reason we're, again, kind of beating this subject to death, the identification of what structure has been modified is super, super important. These are your pedipalps. Okay, so if everybody can see that on your screen, the parts that are red, pink, and white, this is the food manipulation station. That sounds cool and it rhymes. This is a modified appendage, but not really used for feeding, more used for food acquisition. These are the chelicera. So pedipalps, I'll highlight the pedipalps in green. And we'll do the chelicera in blue. Chelicera, the feeding appendages. Pedipalps, the food acquisition tools. On a scorpion, for example, let's get this out of here. This right here, this would be that iconic pincher. The pedipalps or the chelicerae are much smaller and located here. This would be the pincher on a scorpion. With this animal, again, because why not just have an absurd exception to all these rules just to make things look weird? You got to have it. It's kind of par for the course when you talk invertebrates. Again, we're talking 80,000 species here. We're going to have some outliers. But here we have extremely enlarged chelae, much smaller pedipalps. So brings us to the pedipalps. This is the second pair. And again, I'm asking you guys to bisect this animal, basically. Start midline of the mouth and head and work your way both clockwise and counterclockwise out. The second pair, as you fan out, those are your pedipalps. So no matter what, the appendages closest to the mouth are the chelicera, no matter what. The next pair out, no matter what, those are our pedipalps. So the second pair, we see tons of modification here too, obviously, between especially spiders and scorpions. That's a big one, but a lot of diversity here. From the pedipalps as we radiate out, again, in that both clock and counterclockwise pattern, the next appendages we get to, these are the walking limbs. But they all stem from that central axis where we have chelicera, pedipalps, then walking limbs. So again, two very different species here. Two very different looks, especially with the pedipalps. Here, 1, 2, 3, 4. Okay, so we've got 4 pairs of legs. This is your pedipalp. This is your chelicera. Give me 1 sec while I try to pull something up real quick. We're having some computer issues today, guys, so I'm trying my best here. But, oops, let's get all those drawings off there. This image right here, hopefully that's showing up on everybody's screen. It'll show up in the recordings either way. Is an excellent example of what we're looking at. This exact diagram or something very, very similar to it will show up on future exams possibly. So I would jot this down. A couple things to look at when we start diving into the anatomy of these animals. First off, when we, again, pedipalp and the chelae or the fangs right here. One of the things to look at too when you're dealing with invertebrates, and this is super important if you plan on interning maybe at a facility like Butterfly Pavilion, is identifying how we label these animals, various features, colorations, patterns, almost like a fingerprint. If you were talking about a spider species, a tarantula especially, it'd be really difficult. Let's say you got an injury here. Maybe they're communally housed, maybe it fell. Let's say you had an injury to this leg. It's very difficult to discern if you said its third leg is broken. That could be on this side, or if I was counting the other way, it could be on this side or this side. So we literally, well, I guess not literally, figuratively, bisect the animal, and we label everything like this. Leg 1, leg 2, leg 3, leg 4. It will be leg 1, leg 2, leg 3, leg 4 on the other side of the animal. And a couple of reasons for this. One, we can tell right away, leg 3 on the right side if there's an injury. With a lot of species too, there's always color identifying markers, again, kind of like a fingerprint. We can say, hey, if you want to know if this animal's a male or female, check for a yellow spot on leg 3. And we know on both sides of the animal, that spot's going to show up. So it tells us a lot. It allows us to identify everything from a bad molt to defining characteristics, to colorations, patterns, things like that, injuries. And so let me click all this off for a second. so you can actually see the picture. It tells us a lot about how these animals are built, labeled, and more importantly, the part I like about it is this tells us a lot about how much has been sunk into the husbandry of them, where we do have a newly formatted system of how to care for these animals, how to label them, identify, again, injuries or colorations. Uh, Anytime we see stuff like this, I think it just speaks volumes to the countless hours and work and the. If any of you have ever had a paper peer reviewed, you know the torture of it. Um, I know I certainly have lived that life. Um, Getting papers peer reviewed, kind of like this, uh, where there's disagreements and objections from the court. Uh, when we finally settle on something like this, it does speak volumes to how much husbandry and countless hours of work, mostly by zookeepers, probably unpaid, have gone into how to identify, how to label, how to look at some of our invertebrate species. So it is relevant, but really important with this identification process. Another thing while we're here, I want to point out, we just talked about this is the cephalothorax, this is the opisthossoma. This comes into play when you were talking about tarantulas and spider species. Uh, while, yes, this is the cephalothorax, because of what this magical little piece here, the pedicel, let me show you another picture of that. The pedicel, it's the spider waist. Because of the pedicel, it gives us two new names. So yes, we've got cephalothorax, yes, we've got abdomen, but really it's opisthossoma. The pedicel is never exhibited better than, sorry, I'm trying to get my pen to come back up and it's not. That's fun. Okay, well, I can't get the marker to come back up. I'm sure you guys won't mind me not drawing stuff. But exhibited really perfectly in the Black Widow, where we've got this huge abdomen, very tiny head. The pedicel is kind of that cutoff. That's like the, I don't think anybody does this anymore, but if you do, bravo. Like the wristband, the hairband that people used to keep around their wrist, something to tighten off. It's kind of that restriction from the body to the head, where we have a immediate cutoff in size, shape, and structure, just in general. So the pedicel makes it go from a cephalothorax and an abdomen to a prosoma and opisthossoma. Again, we'll talk about them when they pop up, but typically your abdomen is going to lack all of the appendages. They might look like they stem from that back section of the animal, but they should all be attached to the thorax. If not, they're definitely specialized. It's a unique animal. Something weird's going on. The abdomen itself typically houses all the internal viscera. Uh, this is your digestive tract, reproductive tract. It's going to be where you respirate. It's the powerhouse. It does everything. The rest of the animal is there to get food and then give it to the abdomen. The abdomen's the key housing unit to keep these animals running. So now that we've learned everything about tarantula anatomy and how they work, why not look at the weirdest of the group? That's basically a complete outlier. While horseshoe crabs are weird, Xiphosaura offers us an insight into all terrestrial chelicerate and a lot of just invertebrate in general anatomy. Oddly enough, as weird as this animal is, and hopefully you guys have all had a chance to encounter one. If you haven't, I don't know what to tell you. They're weird, man. They're super cool. They're horrifying. The top does not match the bottom. I mean, they scare people, but they make cool touch tank editions, and they are beyond fascinating and have contributed so much to humans in general. You guys might not know it yet, but they're responsible for a lot of stuff. And yeah, we'll get into, we'll definitely tip our hats to them towards the end of this. For the most part, the again, if you've encountered these animals in your personal life, more than likely you've been in contact with an Atlantic coastline animal. There's 4 species. The North American Atlantic horseshoe crabs are far and away the most displayed, exhibited, and utilized both in zoos and the biomedical field as well. So they're going to get their name here from the horseshoe shape they exhibit. That's only true from the top side. Once you look on the ventral aspect, so the underside of the animal, completely different setup. The top looks very unassuming, almost like the what's that old movie, Predator mask from back in the day, the old 80s movie. Very simplified on top, does look foreign and weird, but certainly not threatening. Flip them over, and yeah, we're in a whole new ball game now. We've got a unique chance with these animals to understand, learn, and hopefully educate from them, with the fact that basically what we're looking at is an already dissected terrestrial invertebrate. So what I mean by that, and again, hopefully you have or will have a chance to experience this with these animals. When we look at the ventral aspect of a horseshoe crab, so we've flipped one over and we're looking at the underside. Yes, you're looking at like a terrifying alien face hugger monster, but you're also looking at basically a bisection of a terrestrial invertebrate. Everything we're going to see looks, it's like getting an inside view or a sneak peek at other animals. All the parts are basically going to be the same. Picture, and again, please don't do this at your facility, you will get fired. But if you smash 2 horseshoe crabs together, belly to belly, if you will, that's basically what a spider or a scorpion is. It's legs, it's gills. Now, when we encapsulate it, it becomes externalized legs, internalized gills. It really is like looking at a cross section of a terrestrial invertebrate when we look at a horseshoe crab. So there's a lot to learn from them. We've got, again, because they're chelicerates, and just so you guys know, like, this has been signed off on, thumbs up. They got the cool red stamp. 1,000,000% now. Horseshoe crabs are basically arachnids. They've always been chelicerates. Now they're basically just aquatic spiders as far as their classifications. They do look vastly different. I know nobody wants to find one of these in their basement. I'm sure you guys are freaking out thinking about the wolf spiders and cellar spiders that you have. Nobody wants to come downstairs and find a horseshoe crab scuttering around when you flip on the lights, or one in the bathtub. That's where they always seem to end up. Just FYI, if you do have a horseshoe crab in your bathtub, call me. I'll come pick it up. It's a weird situation, but if you find yourself there, let me know. Shy of that, though, despite their appearance, they're literally just aquatic spiders. All the parts the same. The labeling, the identification, and the function of all their both internal and externalized organs. It's a bisected aquatic spider or scorpion. I think the unique learning opportunity with these animals is that they've remained relatively unchanged the whole time. They are what we call living fossils. It's probably a term you've heard before. Living fossils, an animal that has not gone through a lot of adaptive radiation throughout the years. And by years, I mean like millions of them. So I don't know, it provides us a cool, unique look at a snapshot in time of how invertebrates really transition to terrestrial life, all by looking at the horseshoe crab. So there's a ton to learn and gain from these animals. Here's the underside, again, 2 slides back. Oh, it looks pretty cute. Aside from the crazy stinger, looks relatively harmless. Then you flip it over and get this view. Not nearly as pleasant. There's, if any of you have ever felt one or been able to hold one, it's, I can't even describe the feeling. It's like a really wet feather that has pinchers at the end of it. The underside of these animals, it seems like, for those of you that like have a anxiety about like too much stuff going on, this would be the animal. On the underside, it feels like just pinchers and feathers, and like it's like, whoa, slow it down, guy. There's a lot going on the underside of these animals. There's textures and weird movements and everything you could ever imagine in your little nightmare escape. That's going on underneath the horseshoe crab. There is a ton of moving parts, literally and figuratively. But what we're going to focus on is both the brachial chamber and the genital opercula. So the opercula begins down here. We basically have a flange, if you will, an area where the reproductive gametes are going to either leave or come into. Again, the thing I want you guys to take in, because this is weird stuff, we're looking at the abdomen now and the book lungs. Book lungs sit underneath the genital opercula. So this is all the book lungs. The thing I want you to keep in mind for all of this is if this horseshoe crab had this looks like a halfway done 3D drawing, right? Like maybe we've only printed out half of it. If we print the other half, again, almost like sandwiching 2 horseshoe crabs together, what you're doing right now is, yes, looking at a horseshoe crab, but you're looking inside of a spider or scorpion species. This is like a bisected version of it. It's like we're doing a dissection in class, but we can just see it right here. They haven't completed the 3D printing job to close off the rest of the animal. So yes, we've got to learn about it, but really what we're doing is learning about the inside of all the other terrestrial invertebrates, because they're just a filled-in version of a horseshoe crab. The telson, we have to get this out there, has nothing to do with intimidation or poison or toxins, anything like that. I'll give it to them. It does look intimidating, but it's literally made just to right themselves, so to flip over. That's pretty much its only function. This does not belong in the same category as, like, I had to throw one up for my boy, stingrays, and like this a Steve Irwin type situation. And you know Steve, he wouldn't even be mad if it was a horseshoe crab. He'd be very excited to teach you all about his telson. So while it does look intimidating, it has nothing to do with toxic defense or attacking people. It's literally just a turnover. So and now we're kind of getting into the nitty gritty underside of these animals. Like I said, it's a lot going on. And a lot of that has to do with the gnathobase. The gnathobase is the coxa, or the terminal end. The first segment of these animals have, and again, we're looking from the end of the animal up to the body. We have, I want to say, pinchers. It's probably the best way to describe them. Kind of like lobster claws, not nearly the dexterity. It's just a bunch of, you know what, probably a good example. They're like chopsticks. They're going to be able to manipulate and move food, but not nearly as well as, like, let's say, a spoon would. So you're able to pick at stuff, not in huge volumes, but because you don't have a mouth, that's pretty handy. You're able to basically use these pincher chopstick type utensils and start picking pieces off of whatever prey item you're about to consume, and start moving that towards the mouth. It's the only chance you get to chew So it's important that these nathobases are small and direct, and again, almost beginning this chewing process for the animal. The nathobases form one of my favorite terms in invertebrate zoology, and that is the term food groove. It's scientific, you can use it. Um, I have no idea how you're going to apply that in your home life. I know with quarantine, everybody's hit their own food groove at some point. Uh, just get into it. But here we have a true scientific food groove uh, with how these animals eat. Basically, they have this, and again, it's like a wet feather, guys. I don't know how else to describe it. Like if you're if you've done an internship yet and you've had to sweep down a barn with somebody else hosing it off, or you have a hose or a pressure washer, that feeling you get when the broom's wet at the end, uh, that's kind of what this is like. It's a very bristly, complex system of what feels like bristles, feathers, fingers, every weird thing you can imagine. Um, Again, it's anybody with like anxiety's worst nightmare. It's a lot to take in. Uh, this whole furrow, though, is forming what we call the food groove. And as these nathobases, so the terminal, we'll use tweezers. Let's use tweezers. As these tweezers start plucking little pieces off of the animal, it feeds them to the food groove. All these feathers and filaments and bristles start working all of the, again, I don't want to say chewed up, but pieced out food up towards the mouth so the animal can consume it. So it's basically a giant walking stomach slash mouth. The entire organism is designed to crush, piece out, uh, take apart, dissect, almost masticate um, food from underneath them, and then feed them to this horrifying broom monster that lives in their stomach. And then that moves it towards the mouth. It's very weird. I get it. But again, does anybody have any questions at this point? I know I've used a million different weird analogies. Weird chopsticks that tweeze the food out. It feeds it no matter what to the groove here. And then all these filaments move it towards the mouth where the animal is able to consume it. Any questions about any of this so far?
Yeah, I do. So are they basically just constantly feeding while they're walking, or are they seeking out food and just like walking over it and absorbing it, or like do they like purposely feed, or are they just constantly kind of ingesting while they're walking?
Yeah, excellent question. I wouldn't call them voracious predators by any means. One of the things you got to think about is uh, first off, what these animals are sensing is more than likely an ammonious or nitrogenous compound being released into the water from a waste product. So let's say you have a worm, a polychaete, something like that, in the sand. It's releasing waste, breathing its normal course. The animal is going to detect waste gases and can move towards that. But as was mentioned, they also do quite a bit of that kind of grazing. Um, and it's almost a hand in hand agreement type thing. As the animal moves, it's obviously going to be churning up soil already. If as they filter the sand, if some organic particulate is stored or found, that of course gets fed up to the nathobases. Things like, and again, I'm simplifying it here as much as possible. Understand there's a lot more complex pattern that happens. But yeah, let's say you're cruising along, stumble upon a bunch of algae mixed into the sand. The algae moves up uh, into that food groove. The sand gets deposited. Of course, there's more stuff than just algae, more stuff than just sand. We've got a myriad of substrates. And I'm glad that question was asked because think about the crazy amount of diet. Like it's like the world's craziest buffet. Think about the crazy array of food sources these animals come across. They're very active. They're constantly cruising along the ocean. It's not like we're talking sponges that stay in one spot. You might come up on algae, sand, obviously pollution now. So you could come across a jug of an old milk jug, a whale carcass, some algae. Like you've got to be a very very much a generalist, which is probably why these animals have been around so long. So it's a great question. It's hard to answer. And I'm not going to tell you guys I know the answer. Uh, I will tell you my opinion. I would not say that they actively predate. Um, I'd say they almost like I know that's how I've been during quarantine and COVID and all that. Like, if you go by the fridge, like, oh, I'll grab something, but I'm not actively going to the fridge. Uh, Certainly, if the animal's hungry, it has the detection system in place to seek out a food source. But these animals are typically moving around enough; they're going to just find something. Um, so, yeah, great question, and I can't put a solid answer on it. They are effective predators when they need to be, but more than likely they're just casual snackers. Um, I think is a good way to describe them. They'll go eat when they need to, and they have the detection system in place should they need that. But they're not actively. We're not going to see Shark Week with them taking down a polychaete anytime soon. Um, so they've got the best of both worlds. Uh, they basically just move, and as they move, they can consume. If they do get hungry, they have something there to help them out in that regard. But excellent question. Um, so yeah, I would say they're more just all of you at home walking by your pantry and refrigerator, like, oh, I don't really need a granola bar, but like I'll snag one on my way. Go back to the TV and like I don't need to eat this, but let's go for it. And then when you are hungry, you do have the ability to go to that pantry and make a meal. I hope that answers the question, but really good. So got another question about the husbandry and the design of their enclosure. Uh, they do need sand. They like to burrow. Burrowing's odd, obviously, because your top already looks pretty armored. The fact that you would burrow under sand to protect your underside, which is horribly formidable, um, is odd as well. But husbandry wise for these animals, typically just flat sand works out very well for them. They do not seem, again, I'm not anthropomorphizing. They don't seem to really seek out like rocky outcroppings and things like that. Um, you don't see them too often in hiding spots, which makes them wonderful display animals. It's probably why they're in so many touch tanks around the world. Um, Flat sand, very minimal. You don't want, for starters, you don't want a bunch of decorations like live plants in there and things like that. So very minimal setup when it comes to um, the true husbandry and keeping from what we know. Again, I'm sure there's more work that can be done, but these animals are regularly farmed too, and their setups are very minimal. Uh, they're as basic as it gets: uh, sand, water, and some food. Um, which right now I'm sure to all of us coming off spring break, like that's kind of all I wanted spring break too, was just a nice beach, some sand, and some food. Call it good. Uh, the the one thing I do want to say, I don't want to be passing this off like these are super easy, um, basic pumpkin spice latte UGG boot, like basic animals. There's a lot going on here, guys. Yes, they're casual snackers, aren't we all? Yes, they need the most minimal setup ever. I think we've all found that with the COVID crisis. Um, there's a lot going on here, and in like I think 2 or 3 slides from now we'll see it. I don't have my other screen up, but there's a lot to these animals. So while I do want to say like yes, they require minimum setup, they do require still the same amount of care and concern that any other animal would. Uh, I just don't want to paint them with the brush of being an easy animal. A lot more going on here. Quickly, the gut. We're not going to spend a lot of time here. Anytime we see this J-shaped gut, it usually tells us the animal has a very simplified digestive tract, meaning more than likely, and again, I want you guys to think back to animal bio, mammals, maybe any of the other courses you might have taken. The more complex the stomach, it usually tells us that the animal's more on the vegetarian side. You need a more complex digestive tract when processing only plant matter. Your omnivores or your generalists are always going to have a simpler digestive tract because they can just eat anything. It goes in and out, the end. And these animals fall into that category. Extremely simplified gut. They basically use all the food that goes through them and separate out the components that they don't need. Some of this transfers in the feces, some of it through the gills, but very simplified digestive tract. Again, usually a good indicator that the animal's either carnivorous or omnivorous, and that's the case here. One of the things that's been, excuse me, one of the things that's been a kind of a saving grace for these animals is that they're not edible. They're very prevalent. They're all over the place and could very easily fall under the category of a shellfish / seafood. I have seen them, not personally, but like on shows and stuff. There are some both cultures and nations that do consume them. I personally have never. If anybody has seen one, let me know. Chime in. Never seen or been to a restaurant or a place that serves them, but they do show up on menus. One of the main reasons, however, that they don't show up too often is because of what we call saxitoxin or STX. When you hear about shellfish poisoning, I think it kind of comes up just in conversation casually. Personally, I don't know anybody that's actually been afflicted with this, but it is a very real thing. I assume being in Colorado, a landlocked state, we're not going to be fearful of this for a while. But think back a billion lectures ago when we talked like bioaccumulation. These animals literally sit on the bottom of the ocean for their entire lives, consuming everything that's fallen to the bottom of the ocean. Again, we know about the rule of 10, the energy flow, but then the biotoxins they're accumulating. So these animals are basically sponges for everything that could be potentially not floating, but resting on the seabed. So they're perfect magnets to just soak up a lot of this STX, and it results in what we call PSP, or paralytic shellfish poisoning. It's always a mouthful. I think a while back, like Jeremy Piven got it or something. I'm not trying to downplay it like it's not a big deal. It doesn't ring true in our lives nearly as much, just because a lot of people aren't as exposed to it, and a lot of people don't eat enough shellfish for this to occur. But again, keep in mind, guys, think about that bioaccumulation. Just because you're not getting PSP, like you're accumulating all those toxins. This is not, if any of you like have dates tonight at Joe's Crab Shack, I'm not trying to make you cancel your reservations. Not trying to ruin anybody's evenings, but all this stuff, especially from the ocean that we consume, while yeah, right now we might not have any side effects, no matter what, you're going to get 10% of the energy from that fish or shellfish. You're getting all of the toxins that animal has accumulated over the years. And again, guys, I'm seriously not trying to change anybody's dietary plans. Last night we cooked a gigantic ham and asparagus, and like I don't want to know where my ham comes from. I know it tastes good with brown sugar. Like, let's do it. So I'm there with you. I'm here. I'm an ally for your horrible eating habits. But just something to keep in mind with that bioaccumulation, the buildup of toxins in the body. This is where I put that asterisk on the animal being kind of basic, if you will. The horseshoe crab might be one of the most useful animals ever in American history, certainly in the medical field. And it all stems from, again, guys, I don't know how this stuff happens. I just go off of what I know. I wasn't there day one when we decided, hey, let's pour horseshoe crab blood into a vaccine and see how it turns out. But what we do know is because these animals, maybe we should start back a little further. Let's back it up a second. Let's start with the hemosyl before we get into the bloodstream of these animals. The hemosyl is basically, do you guys remember when we talked cephalopods and we talked that closed circulatory system? I told you how advanced it was for an animal like that. Now we've reverted back to that hemosyl stage. Hemosyl is literally just a giant cavity where the blood almost just sloshes around. Um, the blood moves around freely. The animals are able to not as directly, but still regulate various processes, distribute nutrients, distribute oxygen, things like that. But now we've almost reverted from that closed circulatory system to an open cavity that just has blood going all, I think, willy-nilly is the term we'll use. That sounds cool. Typically, you need a much more voracious lung and heart system because you don't. So, for example, you don't know if the blood sloshing back towards you is going to be oxygenated or not. So typically, you have much more. You have smaller chambers and more of them versus one big heart that knows where the blood is going. If that makes sense to everybody. Within horseshoe crab blood, however, we found what we call hemocyanin. Two types of this. So hemosyl is the cavity where the blood is stored. Hemocyanin is basically the term for arthropod blood. And horseshoe crabs have a very, very unique one. Hemocyanin, basically, we've divvied it up into two parts. One part we know is for clotting, and the other part, these hemocytes work in a myriad of ways. It's not fair to compare it to like red and white blood cells that we would typically associate with humans because it's so much more complex. Picture an animal that has a very shortened gut, lives along the bottom of the ocean, has been around for hundreds of millions of years. So eating God knows what, from trash, debris, decaying matter, live matter, hunting, algae. Like you can't, if it's in the ocean, a horseshoe crab's eating it, dead or alive, organic or inorganic. These animals have kind of been through the ringer when it comes to dietary preferences. So one of the things their bodies have developed over these millions of years is a detection system. Their blood, their hemocyanin, can detect whether a single bit of bacterial or fungal infections have occurred, which makes sense, again, given their dietary lifestyle and the fact that blood's everywhere sloshing around that hemosyl. So here's how it works. And again, I don't know how we come to these conclusions, who started this study, but it works. And now with the craziness that is our world here in 2021, relevant now more than ever, the horseshoe crab, if you've ever had a vaccine in your life or a shot of anything, so this isn't even like a anti-vaxxer statement, I'm not doing anything like that. If you've ever had a shot at the doctor's office, you have a horseshoe crab to thank. We found that their blood is so effective at picking up the slightest toxin abnormality or bacterial infection. We basically run all our vaccines through horseshoe blood, or more realistically, we add horseshoe blood to them. That tells us if the batch of vaccinations or shots or medicine, anything, does not have to be a vaccination, but that's the most relevant usage for them. If you've had a shot, it was tested first with horseshoe crab blood to make sure that it wasn't either a bad batch, a dud, maybe had a bacterial infection. They're arguably the most important animals we have in the biomedical industry today. The analogy I always use is it's very stupid, but kind of relevant. It'd be like having a batch of, like, you're cruising around, you go to Taco Bell, you have your jug of horseshoe blood. You could put a few drops on your taco or burrito and see, am I gonna get sick tonight? It would be your like clear indicator of whether or not that food had been out under a heat lamp for 10 hours and shouldn't be consumed, or whether or not it was like made fresh. This is not a knock on Taco Bell. This is going online on YouTube. I am sponsored by Taco Bell. Please try the new Grande Chalupa box. I have to say that I get $5 every time. But it would be the equivalent of going out and being able to test all your food for infections immediately. That's what they're able to do for vaccines, for shots, for, I mean, down to painkillers, down to numbing, injections, anything. If it's shot into your body by a doctor, you have a horseshoe crab to thank for it, because they're the ones that are doing all the testing. This is the process that you see here on the right of your screen. They basically fold the animals in half, and I don't know if anybody here has ever seen it. Maybe some of you have done it. That'd be cool. Ever tapped a tree for sap? You basically just hammer a spigot into it, turn it on, and let the sap drain out. That's essentially what we do with the horseshoe crab. You fold them in half. They put them in the mechanism that you can see on the right side of your screen that keeps them kind of pinned that way. And then, I'm not knocking anybody in this field, but you gracefully jab a needle into the back of them and then let their blood drain out. You can see it is blue in nature, even once it becomes oxidized. Another unique trait to hemocyanin. If you guys all right now look down at your arms and wrists, our blood is blue in our bodies until it gets exposed to oxygen, then it turns red. The hemocyanin or hemolymph remains blue for a lot of our invertebrate species. So next time you're out, if you're going to go get the COVID vaccine, high five a horseshoe crab on your way to the doctor's office. That's my PSA. All right, we got a little bit of time left. Here we're going to look at book gills. The reason we're looking at this right now is because, again, this is the best example I can give you of what a terrestrial invert's going to look like. Just picture it sandwiched up and the rest of the animal's completed. This looks exactly like if we cut a tarantula in half. If we were doing a dissection, this is a great opportunity because it's like looking inside of all the other invertebrates we would talk about. We have the genital operculum, of course, and then our book gills right here. The first section here is usually the largest. These are the genital operculum. It covers up the gonadal tissues, but then the second section is our book gills. With these animals, and again, I know this is a very repeated thing for me, but it's important just to always keep in the back of your mind, so I'll say it again, and I won't feel bad about it. Anytime we can breathe and move oxygen or nutrients to or from a location, we can also disperse of waste gases, nitrogenous compounds, things like that. So waste, for the most part, is going to be removed from the gills. It just leaves the bloodstream. First off, it's so much more efficient. It's like not having to go to the bathroom, but getting rid of all that waste anyway, just by breathing. Extremely, extremely effective. It does serve, as we've seen so far with gills and breathing, a myriad of functions. You're taking on oxygen. You're expelling waste gas. You're able to assist your body now with, like we talked about with cephalopods, dealing with various salinity contents of the water. So osmoregulation in brackish waters. Very, very efficient animals, despite all the primitive properties they seem to exhibit externally. Real quick, we can talk about nephrotic real quick. This is one of those weird just add-ons. It's not important. I mean, it's not important, but probably not test worthy. But this is one of those times we find kind of those weird connecting points of human anatomy to that invertebrate life where we all stemmed from. And that's with the nephrotic tubules in the kidney. it basically ties us with horseshoe crabs, hagfish, and annelids. And it's kind of one of these like little throwbacks, like a what do you guys call them on the movies nowadays? An Easter egg, something you can go back and look at and really find a true connection. Uh, Looking through chat, we've got another question. Our blood being oxygenated in our bodies, and yes, it is. Of course, it is. It's between the heart and lungs. You guys obviously know your veins and arteries. Veins going back to the heart, arteries going out from the heart. And so, while yes, our blood is oxygenated, the exposure to just free flowing oxygen, that's what gets your blood actually turn red. Um, I don't know a better analogy, like almost like how a lobster turns red when it's in boiling water, but they're not red. Um, I don't know, some analogy like that. I'll think of a better one as we go. But yeah, that's why your blood looks almost blue in your like the veins of your arm, for example. But everybody obviously who's gotten an injury or cut or scrape knows that after it comes out, it's immediately red. It's that overexposure to oxygen. But the dissolved oxygen in your blood will not affect that change. CNS, they've got a central nervous system. Sorry, guys, I'm going to try to go fast through the rest of this. The main thing we want to get to is the book gills. The book gills are going to tell us everything we know about terrestrial inverts, because eventually those are going to switch to book lungs. The eyes are another spot we can observe what terrestrial invertebrate life is like. They have these compound eyes with one of my favorite terms in invert zookeeping, ommatidia, a term you've probably heard before. It's if you guys picture a nature documentary where they zoom in on a fly or a bee, it's kind of that hexagon or octagon shape on the eye where there's a bunch of them. You're never getting a solid image, but you're getting a ton of movement detection. So you're never able to, it'd be like being in class. You guys remember what that was like? Being in a classroom and never being able to make out anyone's face, but knowing if someone was coming towards or away from you, a shadow above you. So no detail, but good movement reception. And from that, you can form kind of that knee-jerk reaction. If I know a shadow's above me, I have to move. There's the compound eye. Again, it's just a bunch of micro eyes that are all designed to pick up shadows and movement, nothing in detail. This is a term you guys have heard before. I know it. It's gonochorism. Gonochoristic animals, meaning being at least one or being one of at least two distinct sexes. Very strange breeding style here, but very logical. Again, these animals have millions of years of head start on most other creatures, so they know what they're doing. Very specific mating seasons. Basically, what we have is seasonality dictates it, but males and females will both aggregate basically on shore, if not intertidal on shore. The mating behavior here is very chaotic. It's not just a pair links up and goes on their way. Basically, what we have here, let's see if the pen works now, I think. Yep. Basically, what we have is the females find a spot on the beach they like. They'll dig a hole with their pusher legs, and she'll kind of settle in with a depression in that sand. She starts depositing eggs almost immediately, and males will constantly, it's not just a male, males, plural, will constantly clamor over her and fight over her, grasping onto her and releasing their respective sperm into that kind of depression in the sand. But because you can see how many animals are here, the females are the ones lodged at the bottom. Males constantly are battling for supremacy, for mating. Yes, it's chaotic. It's not like nobody's getting a good, I don't know. Do you guys leave stars on like your Tinder apps? I don't know how that works. You're not getting 5 stars on your dating app. Just a sec, baby. I'm talking about horseshoe crabs breeding. Yes.
Daddy, guess what?
What?
My movie is over.
Is it really?
Yeah.
Oh, I'll be right there. All right, so we've got an update on the movie situation. Now that we've done that, one of the advantages to this chaotic breeding style is, of course, that you get a single female can deposit a clutch of 30,000 eggs and have, let's say, 15 different parent species. The fathers of these 30,000 offspring could be clamoring all over the place, depositing their respective sperm and increasing genetic diversity within a single clutch. Again, one of the things to always keep in the back of your mind is when we look at a simple animal like this that is quote unquote primitive, genetic diversity isn't that important. We don't need it's kind of one of those if it's not broke, don't fix it type situations. These animals clearly have done very well for themselves throughout the years. We don't need a lot of mutations and a lot of diversity here. We just want to keep this same model running. So that helps in that regard. As far as sexual maturity, it does take a long time, which is why the medical field has now started some actually conservation-based studies with these animals, trying to make sure they do stay alive so that we can keep utilizing their blood. When you have a 12-year sexual maturation period, it's not like you can just go pluck them out of the water, drain their blood, and call it a day. Like, we need to think about the long term here. So they are farmed now, and we've learned a lot more from that, especially given the fact that you're 12 years out from your next batch. This is just on here for giggles, because who doesn't love seeing babies? The larvae are called trilobite larvae. Just a second.
This is amazing.
It's amazing? I didn't even pay him to say that. You think that's amazing?
Yeah.
Yeah.
I don't know why are you looking at different animals.
Well, that's what I do. That's my job. Thanks, baby. Can you go out there? I'll be right back.
Sure.
Okay? All right. This is what you get when you record stuff from home. Larvae, adorable. We're looking at different animals, apparently. They're called trilobite larvae. And really what's cool about the development of these animals is once they're born, they almost are complete horseshoe crabs. The only thing that grows out of proportion, everything else is going to grow in proportion, is the telson. Their tail is going to grow longer as the animal gets older, but really pretty solid. Pretty good form of direct development. All right. Let me see if the thing's on here. Oh, it's a different video. Hang on a second. And my computer is not cooperating today. All right. Guess we can't pull that up. I will make sure I post a link for the video we're going to watch too. Not super important, but was relevant. So now we're going to get into the arachnids. We don't have much time left, so I'm going to go as fast as I can. Again, I'll post this afterwards, and you guys can, of course, always email me, or we'll talk about review questions over the upcoming weeks. So go through this pretty quickly and try to touch on everything at the same time. Huge myriad of species here. Again, I think the one that gets unlisted quite a bit is up here at the top of your page. These are animals that no matter what, I get that people are grossed out by spiders and scorpions and don't want to ever work with them. Guess what? You're still going to be working with arachnids. If you have a dog, if you have a horse, if you have any mammal in any state, anywhere, you will eventually deal with ticks, mites, fleas, things like that. No matter what, it's going to pop up and be a cause of concern. So believe it or not, the husbandry is still important of them. one of the weird things we find with arachnids is we have an excretory system that, put simply, is very, very similar to what we see from reptiles and amphibians, where we have a conservation of all the water in the environment, and the waste product will be just that. It will be waste, not any dilution. The Malpighian tubes serve basically the same way that the terminal end of the cloaca does in a reptile, where waste moves through the body. At the very last minute, the water is sucked out or extracted and kept within the body, and only the waste is deposited. Meaning, if you, let's say we're keeping a tarantula, for example, you might find little to no waste. And I don't know if anybody here has a tarantula or a scorpion or something like that. If anybody does, let me know and you can confirm my statements. It's very doubtful, though, you've picked up fecal matter out of your animal's enclosure. They're extremely efficient at just depositing a little bit of just waste and keeping all the nutrients and food with them, and water, especially. Quickly here, we have venom glands with venom with the asterisk by it. This is, I'm going to try to sum this up as quick as I can. Venom for one of these animals is weird. And you guys understand, hopefully I don't have to explain this to you. You guys know the difference between venom and poison, right? Is it venomous or poisonous? If you bite it and you die, it's poisonous. If it bites you and you die, it's venomous. Here we have venom glands. Despite the fact that it's injected, they're typically called poison glands. And the reason being is almost always with every species you talk about that's venomous or poisonous, but let's take venomous for starters. Let's say a rattlesnake and a mouse, okay? The rattlesnake is venomous. Its venom has been designed to incapacitate rodents. With the chelicerates that we're talking about now within arachnids, their venom is designed to incapacitate other arthropods, sometimes other chelicerates. So when you have that kind of conundrum, it becomes a poison gland because technically the venom you've produced would incapacitate yourself. Does that make sense to everybody? I know it's weird, and it is kind of splitting hairs. But it's called a poison gland because the venom they produce is designed to incapacitate an animal just like them. It would be a venom if it was injected into, let's say, just birds or something weird like that, where you have a specialized venom. This would be a poison in this case, which is why it typically gets labeled as a poison gland versus a venom gland. A lot of the times we're going to see those gnatho bases come up. We've already talked about the tagma being connected and the pedicel, or the waist of the spider. That exact picture and diagram is up for you to look at on your D2L, so you can always refer back to that. The pedipalps, that's again the next set of appendages outside of the chelicerae before we start with the walking legs. Again, I always highlight it here because I just think it's such an important thing to be aware of. While almost all of them are carnivorous, we have some that are ectoparasites. Yes, these are our ticks and our mites and our horribly don't want to deal with them from a husbandry standpoint. Thanks, buddy. Don't want to deal with them from a husbandry aspect, but the husbandry of your animals is still going to involve them. So the ectoparasites are another thing to always keep an eye on.
I got on my hand.
As far as the liquid diet these animals are on, it's disgusting. There's no way around it. No way to make this sound any better than it really is. The thing that they've developed basically is almost a stomach that creates a vacuum or a suction. Picture, like, let's say you have a turkey baster or an eyedropper or something, putting it on the palm of your hand, and then you depress it and you release it. It wants to stick or adhere to your hand, right? That's basically the way the sucking stomach works. If you are an arachnid, all you want to do is, again, not chew. You want to break down whatever food you've acquired into a smoothie version and then use your sucking stomach because you don't actually have throat muscles to swallow anything. So you want to create a liquid version of your food and ingest it via the sucking stomach. The book lungs, again, I told you guys this was going to pop up. I still got time. The book lungs are popping up now. These are the terrestrial equivalent of the book gills that we saw on the horseshoe crab. Horseshoe crab having this surface where you have oxygenated water going by. You're able to breathe through your gills. Now, again, let's picture encapsulating that. So 2 horseshoe crabs together. Now we've got book lungs. The key here that I need you guys all to keep in the back of your mind, and sorry for the background noise. The key here is book lungs are going to operate the exact same way that book gills were. Book lungs are filamentous layers that need the presence of oxygenated water, in this case, oxygenated blood around them. And it brings a couple weird things to light when it comes to invertebrate husbandry. It means that if you have, let's just take a tarantula. They're easy to talk about right now. If you have a pet tarantula or a tarantula in your collection and it doesn't receive enough water, it's not going to die of thirst. It's going to die of suffocation. The animal can't breathe unless there's present water flowing through these book gills, which are now book lungs. So none of these animals will ever die of dehydration. They will suffocate first because their bodies lack the moisture to actually keep those book lungs going. So again, that's why I think the horseshoe crab is so relevant to start with. It's like looking inside of another arachnid species, and we're getting the bisection of that animal. Usually, again, not every species, but usually we can see the book lungs themselves, their external appearance. And they do get that name kind of from sitting just like the pages of a book, if like you were flipping through the pages. The pulmonary sinus it surrounds the atrium of this entire both lung, hemosystem, and respiratory system for these animals to actually facilitate ventilation. Yeah, you guys know what the trachea does. Yes, yes, yes. There's the book lungs right here. This is a much better visual for it. And you can see it's so filamentous. It needs this space to kind of have oxygenated hemosil or hemolymph flowing through it. And so again, moisture is going to be relevant here. I don't know any other way to describe it. It's a terrestrial horseshoe crab. It still needs to breathe through these book gills, book lungs. They're different. Obviously, one's moved from the ocean to land, but they're the same organ. They're operating in the same function, in the same capacity. They're both transferring waste. That waste now is getting transferred out of the body, again, with minimal water loss. But it's just an encapsulated version of a horseshoe crab. You guys have probably heard this term before, uricotelic. This is exactly how, for the most part, how reptiles and amphibians, birds are another one, deposit their wastes. Extremely efficient when it comes to removing waste from the bloodstream versus having an organ in place to actually metabolize this stuff. So take us as humans, for example. We have livers and kidneys that filter stuff out, all these things in place. Basically because we have this free-flowing hemosil area where all the blood's just sloshing around. We have the equivalent of a Brita water filter in place with the urocotelic animal. that just sits there, and all it does is capture anything passing by that's a waste product. You deposit just the waste. You don't need the extra, like water, for example, to urinate as a human. We don't need all this extra buildup. It's again, guys, like it's very efficient. You just have blood flowing everywhere. Seems like a hot mess, but then you just stick a filtration system in there that quite literally just collects the undesirable quantities and then passes just those out, retaining all your moisture, all the nutrients, everything you want to keep. This is a very simple version of it, but it's exactly what happens. It's a good setup for these animals. Here quickly is just a image of how some of these animals have manipulated the Malchidian tubes. With some of these Eurocatelic animals, mostly cave dwelling, they've worked out a symbiotic relationship with some bacteria and their own waste products, where basically their own urea glows in the dark. You basically create your own. If any of you guys have had the moth zapper, if any of you had those or have those now, your own waste product is providing your food source. You create a moth zapper, except you're the zapper. So even cave dwelling arachnids have developed really efficient ways of metabolizing their waste and then taking it a step further now and making the best out of those waste products. Sorry, guys, I know this is going to be quick. Again, you'll have all this. It'll be posted, and we can certainly go over questions next week. Again, that term gonochorism coming up again. I know I've hammered on gonochorism a lot, but it's a lot better than learning every one of these. A lot of these typically lend themselves more to botany and how plants reproduce. But this is where we get our roots in a lot of zoological terms and theories. So gonochorism is important, and it's better than memorizing all of these. With reproduction, it's always going to be internal, but the way we have the internal fertilization is going to be varied, to say the least. We have animals with copulatory organs here, or we have indirect fertilization, where essentially a sperm packet is placed on the ground and then transferred into the female's body. We have a myriad of ways of reproduction here. Here's just some of the beautiful shots of arachnids copulating. Let me see. I think this is probably where we'll end it. The reproductive strategies here are very vast. Again, direct or indirect. No matter what, fertilization is always going to be internalized, meaning that the sperm eventually enters the female. Eggs are fertilized in the female, but they're almost always deposited right after. So there's not really it's a way to ensure that eggs get fertilized, but has nothing to do really with parental care. Parental care takes on different roles with all these animals. Scorpions are notorious for carrying their babies on their backs. They exhibit a lot more than, let's say, a tarantula or a spider that has offspring and deposits a clutch of eggs and then leaves. So yeah, it's going to be all over the board here. One of the things, again, this is the unfortunate part of not being in the classroom. The bottom right picture you guys are seeing, working with and having done this for years now and breeding tarantulas, it's wild. If any of you have ever done this yourself or been around somebody that is in this hobby or this trade, there's a lot more going on in that picture than you can tell. It's a very trying time for mainly just the male. The female's basically deciding if she wants to breed or not. The male's deciding if he's going to die or not. Females are notorious for kind of getting halfway into the act and then just in this position here, if she decides halfway through the copulation that she's bored, and again, bored's the anthropomorphic way, she'll literally just let go and then fall down fangs first into the male and then consume him. We have green bottle blue tarantulas at the college that you typically, if you want to breed a female, you need about 8 males because she'll eat the first 7, and hopefully by 8 she's full and she will copulate. It's a trying time. I guess the reason I'm highlighting this, there's so much more that goes into facilitating and keeping these animals than initially meets the eye. Breeding, husbandry, moisture content, all of this stuff, it just seems so easy on the surface, and there's so much more that goes into it. So when we pick back up, we'll talk about scorpions and tarantulas and their ilk and get back into it. But I think that's a good stopping point for the day. I hope you guys enjoyed it. And yeah, there's still a lot more to come, but hopefully that shed a little bit of light on how complex caring for these animals really is.